Hello viewers, good morning. Myself Dr. T.N. Ojha, retired professor of chemistry. Today we are going to discuss a very important spectroscopic method called infrared vibrational spectrometry. This spectrometric method is most commonly used in routine laboratories and in research institutions because its interpretation is very simple. In the beginning, I am going to introduce the subject. In all physical phases, molecules continuously vibrate. Vibrations are mainly of two types. In one, the bond stretching takes place. In the other, bond angle bending takes place. So these two types of vibrations are ceaselessly taking place in molecules, whether it is in gas phase, liquid phase or solid phase. Here I must tell you, while dealing with rotational spectroscopy, I had mentioned that only gas phase samples are good enough for spectrometry, but for infrared vibrational spectrometry, sample in solid phase, liquid phase, gas phase, any phase can be used. It should be dried before use. It should not contain even a trace of moisture. And the infrared region which is used for this spectroscopy is actually 4000 to 667 centimeter reciprocal. This is called mid-infrared region. At a later stage, I will also mention that higher frequency range between 14,000 to 4,000 reciprocal centimeter is mainly used by physicists for the study of overtone bands. The meaning of overtone bands I will tell you a little later. And lower frequency region, that is the range 1000 to nearly 50 reciprocal centimeter, is also used for the study of coordination compounds, because in coordination compounds a metal is bonded to several ligands. Therefore, the metal ligand bonds are very weak. So for their study, we use the far infrared radiation is extending from 1000 to nearly 50 reciprocal centimeters. But for most purposes, mid-IR region between 4000 to 660 reciprocal centimeter is used. It provides a lot of information about the structure of molecules, about rates of reactions, more surprisingly, molecular weight of polymers. And in forensic science and in research laboratories, this technique is also used to confirm the identity or non-identity of two samples. These are some of the points which we need to study in this chapter: energy of infrared radiation, condition for absorption of infrared radiation by molecules and IR spectrum, molecular vibrations, two types I mentioned earlier, bond stretching vibrations, then bond bending, which is also known as molecular deformation, because in bond bending the shape of the molecule is deformed. Then fundamental vibrations. What are fundamental vibrations and what is their number? There we will discuss 3n-5 number and 3n-6 number formula. We will also learn how these formulas are derived by statistical method. Then what are non-fundamental vibrations? If we have fundamental vibrations, the question must come to our mind. It means there must also be non-fundamental vibrations. Then we will discuss about vibrational energy levels, then vibrational energy level excitations, and most commonly for all spectroscopic method we discuss selection rules. Similarly, here also we will discuss selection rules for state transition of molecules. Then display of infrared vibrational spectrum. We will mention there, spectrum is a two-dimensional graph actually. Then in infrared spectrum, we very often use the word peak. What are the peaks and what are their characteristics? Then how infrared spectrum is obtained? The IR spectral experiment, how much sample is required, how much time it requires to record the scanning of one sample, and what type of instruments are used, etc. etc. So these things will be discussed in the spectral experiment. Then a little bit about the energy of infrared radiation. Molecules possess quantized vibrational energy states. These energy states are defined by vibrational quantum number, symbol small v is commonly used, and the values of this quantum number range between 0, 1, 2, 3 up to infinity, whole numbers. Their energies correspond to the mid-IR region from 4000 reciprocal centimeter to 667 reciprocal centimeter. This is the most commonly used region for infrared vibrational spectrometry. The vibrational energy is indicated sometimes by capital E, subscripted small v. V indicates the vibrational quantum number. So the energies of molecules compare with the mid-infrared region. For a diatomic molecule, a formulation of EV is given by 1 over 2 pi c multiplied by under root k by mu. What are these symbols? Let me tell. Mu is reduced mass, as well known. Suppose we have a diatomic molecule AB. Then the reduced mass mu AB is given by the product of the two atomic masses divided by their sum. How do we obtain the atomic mass m? If we have atomic weight, simply divide it by Avogadro number Na. The result is the atomic mass. The another symbol small k, in some of the books you will find small f in place of small k. This is called force constant. In simpler terms, the resistivity or resistance of a bond to stretching is called force constant. Stronger a bond, more the value of K. More polar the bond, more the value of K. Thus, for nitrogen, triple bond nitrogen, K value is the highest. Similarly, for carbon hydrogen single bond, K value is more than carbon-carbon single bond. Again I repeat, if a bond is very strong, then K value will be large. If a bond is very polar, K value will be large. If a bond is non-polar, K value will be smaller. If a bond is weak, again K value will be weaker. The other symbol C, as you know, is the speed of light. Pi, as you know, is constant. So this formula is a classical formula derived for diatomic molecules only. At a later stage, we will learn that this formula has certain discrepancies, but for qualitative purposes, it is okay. Transitions can occur between adjacent vibrational energy states. This is called selection rule. That is, a transition can occur between quantum state V and V plus 1. This will be called absorption mode, or between quantum state V and V minus 1. This will be known as emission mode. Hello, there is some trouble in the instrument. So I will take a break for a few minutes. Okay, thank you. Then we discuss about molecular stretching vibrations. What are molecular stretching vibrations? Stretch means to pull away, pull out. So molecular deformations and molecular stretchings of bonds, these are mainly two types of vibrations. Then we will learn how the formula 3n-5 and 3n-6 are derived. What are fundamental vibrations, what are non-fundamental vibrations, what are overtones, combination bands. All these terms we will learn how these can be defined. Then oscillating dipole and absorption infrared spectrometry. Selection rules. Some of the points I have already covered. Let us discuss in detail molecular stretching vibrations. What is stretching vibration? The definition I have given here. A rhythmical extension and shrinking of bonds symmetrically and asymmetrically such that the bond distance R increases and decreases in succession one after another from the equilibrium distance Re. This is called stretching vibration. If a molecule contains as many as n atoms and its shape is linear, then there will be n-1 fundamental stretchings. If a molecule has two atoms like carbon monoxide or HCl, the above formula n-1 formula says a single stretching vibration can occur. For triatomics, when the number of atoms is 3, the above formula can be applied. N is 3, so 3 minus 1 equal to 2. Such molecules will have two stretchings, symmetric and antisymmetric. Achha, what are the conditions for symmetric vibration or antisymmetric vibration to absorb infrared radiation? We must remember all stretchings may not absorb infrared light. There is a condition. During stretching, the dipole moment of the molecule of the bond must oscillate, that is, it should undergo change. It is not necessary that the molecule has permanent dipole moment, even if it does not have. During vibration, the dipole should change. If this condition is fulfilled, only then that particular mode will absorb infrared light, otherwise not. Then molecular deformations are bond angle bending vibrations. What is the definition? A rhythmical change, that is successive increase and decrease in bond angle theta leading to deformation of the shape of the molecule. Again the formulation, if there are n atoms in the molecule and the shape is linear, there will be a maximum of 2n-4 fundamental bond angle bending vibrational modes. Why I have used the word maximum? Sometimes we find that more than one modes have the same energy. So the instrument will recognize only one. Theoretically, total number of bending vibrations is 2n-4 for linear molecules, 2n-5 for non-linear molecules. Again, the condition for absorption of IR energy is d mu by d theta not equal to 0. That is, during the bending vibration, the dipole of the molecule must oscillate, must change with respect to the angle change. Some examples, diatomic molecules CO and HCl, for them 2n-4 equal to 0. Means if the molecule has only two atoms, the question of bond angle bending does not arise. If there are three atoms in the molecule and the shape is linear, for example carbon monoxide, 2n-4 formula gives the value 2. Two bond angle bending modes. Here you see, if there are only three atoms and the shape is linear, then theoretically two bond angle bending modes should occur. One in the XY plane, another in the YZ plane. But both involve equal amount of energy, that is both are degenerate. Therefore, the instrument will record only one frequency. For non-linear molecules, the value of bond bending vibrations is 2n minus 5. If there are 3 atoms, only one bending mode is possible. For practice, we will take up certain examples. Carbon monoxide, for example. Carbon monoxide has 2 atoms, n barabar 2, n equal to 2. So, number of stretchings n minus 1 equal to 1. That is, one bond stretching mode, no bending. For carbon dioxide, there are 3 atoms, n equal to 3. According to the formula, one IR active stretching, that will be anti-symmetric stretching. One IR inactive stretching. When both oxygen atoms are going away, the dipole of the molecule does not change, it remains 0. Therefore, for carbon dioxide, theoretically 2 stretching modes are possible, anti-symmetric and symmetric. But the symmetric mode is not IR active because during this mode, the dipole moment of the molecule does not change, does not oscillate. When we study Raman spectrometry, I will tell you, in Raman spectrometry, for carbon dioxide, anti-symmetric mode is inactive while the symmetric mode is active, because there the condition for absorption is not dipole but a change in the electrical polarizability of the molecule. And a rule is this: if a molecule is centrosymmetric, that is, if a molecule possesses center of symmetry, then IR active modes will be Raman inactive, definitely, and IR inactive modes will be Raman active. This formulation or this generalization applies only for those molecules which are containing center of symmetry. H2O molecule is non-linear and atoms are 3. So according to the formula n-1, there should be 2 bond stretching vibrations. Here both stretchings, symmetric and antisymmetric, will be IR active, because in both cases the molecule is non-linear. In both cases dipole change occurs and there will be 2n minus 5 equal to 1 bending vibration, which will also be active. Here one more point I would like to tell you. For carbon monoxide, I have told you the antisymmetric stretching will be IR active, and out of 2 bendings, both being degenerate, another information will be available. But when you actually observe the spectrum of carbon dioxide, then 4 bands appear, a phenomenon called Fermi resonance. We will discuss at a later stage. Here I have mentioned a little bit about what are non-fundamental vibrations or overtones and combination bands. Sometimes the vibrational waves combine together and peaks appear at twice the original frequency, 2 nu 1, or even thrice 3 nu 1. Sometimes 2 frequencies may add up, V1 plus V2, nu 1 plus nu 2, or sometimes twice of one frequency minus some other frequency. So these are called overtones. Overtones means twice or thrice the original frequency, and combination means addition and subtraction. These bands or these occurrences have very low probability, but sometimes their occurrence gives some information, supplementary informations, I tell you. So these overtone bands appear where? Above 4000 reciprocal centimeter, between 14,000 to 4,000 reciprocal centimeter. This region of infrared is called near IR. It has more energy than the mid region. Here I have drawn some line diagrams. A diatomic molecule whose bond distance, equilibrium bond distance, is indicated by Re. When it stretches out, the new distance R prime is more than equilibrium distance Re. When it constricts, naturally it has to constrict. When it stretches out, it has to constrict. This whole cycle is called one vibration. This time bond distance become less than the equilibrium distance. So stretching vibrations of a AB molecule, diatomic molecule, are shown, and its frequency formula is 1 upon 2 pi c under root f by mu. As I told earlier, value of mu, that is reduced mass, is calculated by Ma multiplied by Mb divided by Ma plus Mb. What is m? Atomic weight divided by Avogadro number. Here a very important information is given. As I told you, molecules are ceaselessly vibrating. Even in the solid state, they are continuously vibrating. Then what happens? When the vibrational state goes up and up, means a molecule reaches to much higher vibrational energy states, then eventually it may break. And the energy states they don't no longer remain quantized. We reach an continuum. So this is called Moore's potential, a graph between the energy, potential energy, and the internuclear distance R. You see the 0 point axis is shown. The plus means positive energy, negative means decreasing energy, and when two atoms come closer, the potential energy drops until a maximum point is reached where bond formation takes place. If they come more close, then internuclear and interelectronic repulsions cause energy to rise and the graph goes up. So this figure is very important. This figure is available in almost all the books and you must have studied it earlier. But the meaning is, how does a reaction take place? Actually, this is the figure that explains the reactivity of molecules. If a molecule requires more dE, dissociation energy, its reaction will be difficult. If a molecule breaks with a small energy, it reacts easily. Here, I have explained the stretching and bending vibrations using a triatomic hypothetical molecule. So first we will take up linear shape. The molecule has 3 atoms A, B and C. The symmetric stretching is shown. The atoms A and C are moving in the opposite direction. This is called symmetric stretching. Here you must note down, some of the authors use the symbol nu S for symmetric stretching and some other authors use the symbol nu 1 for this kind of mode. The anti-symmetric stretching is shown just below. Here A and B are coming closer while B and C are going farther. This is called anti-symmetric. The symbol here, some of the authors use nu A or nu 3. On the side diagram, we have shown bending vibration. The first one shows bending in the plane. It is called scissoring. The symbol is delta S. Here bending is taking place in the XY plane. Another bending is also possible in the YZ plane, but by simple logic we can understand that both these modes will have the same energy. The reason being, any system containing only 3 particles or 3 points can never be two-dimensional. It is always one-dimensional. So bending in XY plane is same as bending in YZ plane, although theoretically 2 modes are possible, and such modes are called degenerate modes, same energy modes. Now, regarding the derivation of the potential energy formula, I have used a model. A point mass M is hanging from a fixed wall by a spring, and a spring is supposed to have no weight, although this is quite a joke. A spring must have weight, but for mathematical simplicity we have assumed that the spring does not have any weight. Now if a force is applied to the particle of mass m, then it will swing to and forth. From 0 point it will go left side, it will go right. And the Hooke's law says that the restoring force is proportional to the displacement in the opposite direction. Here you see the potential energy is maximum at the two extremes and minimum at the equilibrium position. This graph shows how potential energy increases and decreases. For a system, the sum of kinetic energy and potential energy always remains the same. So at the equilibrium position marked 0, kinetic energy is maximum and potential energy is 0. On the two extremes, kinetic energy is 0 and potential energy is maximum. Throughout this graph, the hyperbola, sum of both energies remains the same. So this is called Hooke's law potential diagram. If we want to calculate the potential energy factor, then integrate dV, again integrate minus k is a constant, x minus xe, that is change in the internuclear distance. This can be replaced by dx. And when we solve this, we get the value Vx equal to half kx square. We must have studied kinetic energy is given by p square by 2m, where p is linear momentum, and the value of potential energy we have just derived, half kx square. So total energy is the sum of these two terms. At a later stage we will come to know that accurate equation for energy can only be obtained from quantum mechanics, h psi equal to E psi. Here the value of the Hamiltonian operator h is mentioned. It is cross h square by 2m del 2 by del x2 plus potential energy term, and below line indicates that when x approaches to plus infinity or minus infinity, psi becomes, wave function becomes 0. This is a necessary condition of limit to be applied. Here I have taken one diagram from my own book, Spectroscopy Molecular Structure. There the things are more clearly shown. The dotted line shows the energy potential for a hypothetical molecule known as harmonic oscillator model, idealized molecule. No molecule is harmonic oscillator. Every molecule is an harmonic oscillator. So the dotted line shows the idealized graph, which is not actual but good for theoretical purposes. Actual graph is shown which is not symmetrical, and dissociation energy is again shown. Here one very interesting information is coming. When we studied rotational spectrometry, I told you that when the molecule is in the J barabar 0 state, that is the ground rotational energy level, it has no rotational energy. But here, in case of vibration, when the molecule is in its downmost energy state, that is V barabar 0, V equal to 0 state, even then it has some amount of energy known as ZP 0 point energy. This is very important difference and very important parameter. ZP, what is ZP? When the molecule is in its ground vibrational energy state, that is V equal to 0, then its energy is not 0. It is ZP, and later we will learn it is equal to half hc nu bar, where h is Planck constant, c is speed of light, nu bar is the fundamental frequency of vibration in reciprocal centimeter units. Here I have shown some of the vibrational modes. Again, this diagram has been taken from my own book. For water molecule, the shape is non-linear. Value of n is 3, total 3n minus 6 modes. What are these modes? Anti-symmetric stretching, symmetric stretching, and scissoring. These three modes are shown. Their frequencies are also shown. The highest value 3756 reciprocal centimeter for anti-symmetric mode and 3652 reciprocal centimeter for the symmetric mode. Both modes are IR active because the molecule is non-linear. The bending vibrations occur at nearly half the frequency. So here the value is 1595 reciprocal centimeter. Below that diagram, I have shown a system having more than 3 atoms. If a system has only 3 atoms, out of plane vibrations cannot take place. But here I have taken the example of methyl group CH3 connected to a carbon. Here the number of atoms is more than 3. So you see several kind of vibrations are possible. The first diagram anti-symmetric, the second one is symmetric, then bending modes in plane and out of plane. Here scissoring and rocking both are in plane, and in this diagram we have shown out of plane vibrations. One is called wagging and other one is called twisting. In twisting you see one atom is going up, the other is going down, whereas in wagging both atoms are going in the same direction. Similarly for carbon dioxide, again the diagram taken from my own book, we have shown stretching, two kind of stretching. In the symmetric stretching you can see the symmetric stretching mode is IR inactive. The data obtained at 1340 centimeter reciprocals is obtained from Raman spectrometry. In the anti-symmetric mode, there is a small mistake in the diagram. One atom is going away, where one other oxygen atom is coming in. So there is a small mistake, please correct it. This mode is IR active because the dipole oscillates during this mode. And below are shown two equal energy bending modes called degenerate modes. The value is 667 centimeter inverse. These are two-fold degenerate modes, and this diagram is applicable to all AB2 type molecule. So here we have shown how can we understand various kinds of vibrations. I summarize. Vibrations are mainly of two types: bond stretchings and bond bendings. Bond stretchings can be symmetric or anti-symmetric. Bond bendings can be in plane, out of plane. The name for in plane are rocking and scissoring. Out of plane bendings are called wagging and twisting. For a long chain molecule, the rocking frequency, rocking peak is very, very significant. Sometimes for a ring compound, the rockings are called ring breathing. Here in the last diagram, I have shown you how the force constant of a bond changes with its structure. The OH bond is very polar, so its force constant is very high, and you see the vibrational frequency is proportional to under root force constant, so its value is nearly 3700 reciprocal centimeter. Carbon monoxide having a triple bond character, again it is very, very high, and the frequency is 2143 reciprocal centimeter. Carbon triple bond nitrogen, nearly as strong as CO, the frequency is nearly 2100 reciprocal centimeter. Carbon triple bond, you see this bond is non-polar. So its force constant is a little lower than CO or CN, a little lower. Carbon oxygen double bond, again a bit lower than CO, but the bond is polar, that is why it is not very low. Just below the data for carbon double bond carbon, you can see it is much less because the bond is non-polar. Now coming to carbon hydrogen single bond, its value is 510 and the calculated value of frequency is 3062 reciprocal centimeter. If you take carbon chlorine, here you may wonder this bond is more polar, but why force constant is less? Because the atom is heavy. And if you calculate the reduced mass, you will notice that frequency is inversely proportional to under root of reduced mass. So chlorine being heavy atom, here the force constant is less. Thank you very much. Thank you.